Hi, class. This is a just a couple highlights for chapter 2, and I'm dividing this into two parts. First part is going to be talking about numbers, and then I'll have a separate video about strings. I hope by now you have at least halfway through the chapter. This is uh, again one of the C++ basics. I hope that it should not prove too much difficulty to you. If you have taken a prerequisite course, CS5. However, I believe there's a new material in this chapter, actually in every chapter, because we're introducing the very latest C++ standard. Okay, so let's just get started. So the first number type we want to introduce would be integers or integral types. And we have seen, obviously, from chapter 1, just a couple of examples of using integers. Integers is probably one of the simplest data types in C++. And there are actually a lot of integral types. So you've seen a lot of examples use int. Now, what int also could be written as signed. Well, if you declare a variable of type int, that actually just means it's a signed integer number. And you can also write more letters. In fact, if you wanted to, could have written signed or signed int, they mean the same thing. Obviously, typically we'll go for the shortest one just to save some typing. So int, typical size is 4 bytes. Now, the way why we're saying this is a typical size, because it's actually implementation specific. It depends on the compiler implementation. So the standard says it needs to be at least 2 bytes. Okay, it doesn't tell you a maximum. Now, why is that? Well, you wonder. Well, originally, when 32-bit computing was pervasive, more of the norm, it was mostly commonly 2 bytes. And nowadays, 64-bit computing has become the norm. So people have raised that to 4 bytes. And that trend could continue. Who knows? Maybe the next common sizes for word, like sort of a words in a CPU architecture, or the size of a registers would be I don't know, 128 bit, or essentially like even more for a typical word in a computer. So anyway, this is not necessarily the most reliable way if you actually care about the number of bytes in that type. If you do care about the number of bytes in that type, there are other types you could use that basically have fixed number of bytes. Now, for the time being, you don't really have to worry too much about that. Now, so int is one of the most common one you would use. And then you probably also are aware of long. Now, long is basically has a bigger range than int. It could be 4 bytes. It could be 8 bytes today. Now, the standard just guarantees a minimum of 4. So you're not going to be sure if it's 4 or 8. Now, there's other alternative type names for long, as you see here. So obviously, long would be preferred if you just write long. And then there's long, long. Long, long, typical size today is 8 bytes. Now, the minimum guaranteed by the standard is 8 bytes. Now, there's also short, which is 2 bytes. That's the minimum. And then you also have the signed char. Now, char itself, usually it's used to represent a character, to hold a character. Now, char is typically 1 byte. The standard, guarantees 1 byte. Now, a signed char, by the way, is a different type. There's also unsigned char. That's another different type. So although they're all 1 byte size, they're actually considered as different types. So yeah, signed char. Now char, even though, as I said, it holds a character, we're going to have a little bit more to say about this in the second portion of this lecture for this chapter. The char is basically represented as an integer. This integer corresponds to the code point of the letter you're trying to represent. And then there's obviously a lot more to say about this. In chapter 1, we'll talk about Unicode. And the again, for right now, just know this is also an integer type. And the ranges of values now, so basically it depends on the size, like how many bytes are we using and whether we're going to use a 1 bit to represent the sign, right? Plus or minus. And so then you can basically calculate the range of values could be represented in that many number of bytes. So this lists the typical range of values for those types. Now, again, typical, that's what you see mostly common today. And the standard does not impose a maximum size. That could change though. So if you are not sure about what your compiler uh, has decided, and then you can query those limits in this. uh, there's a couple of utilities in this namespace, std : numeric limits. The numeric limits. Um, we're going to see an example about this actually. Actually, let's take a look at this right now. So example 207. Just a bit of now before I show you the code for this 207, now this is the code in the book. So I just want to walk you through this. This repo that you have checked out, I have decided to add examples without modules. So you see the named folder for example, you see an example name followed by NOM, short for no module. And so that means this is this is a program you could run on both Windows and Mac because the modules support is a little bit different. For the ones that we need to use modules for the purpose of explaining modules, I'll put those for Mac users, put it into the gcc-modules folder. Now that would not make a big difference to the Windows users because you can run all of those in this normal way. Just use the build to tool. Um, okay, so now for the Mac users, you can also use the build to tool to run these programs ending with the nom. Okay, these are the no module versions. So I have made a slight modification to not use modules. Okay, so this program is the example. So as you'll see here, and there's one thing that's different. There's actually one line that's different from the book. Now the book includes a format library. Now the format library is just a bit of word about format library. We're gonna talk a bit more about in the second part about format. So the format library, just the reason why you see a different header here is I built a standard format function shim to fill in the gap. So right now, this format library is a new feature in C++20. It has not been implemented in all of the major compilers. So can't really use that from the compiler. However, that standard was actually implemented in a separate library that's out there, and the library was the foundation of the proposal for the feature. And so that is what I use to shim this function and to supplement what's lacking in the standard namespace, this std format. Okay, so this is a function call that allows you to interpolate strings, and then we're going to talk about strings a bit more. Now, I just wanted to show you this point about the numeric limits, how you might use them. And numeric limits are in this header limits. Now, here we're talking about headers again. We're not using the header unit module. Now, or in the Microsoft situation, it could be just part of the standard core. Now, unfortunately, none of those compilers, or GCC, MSVC, or CLAN, they don't have that format yet. So anyway, so here, this is the sort of a non-module version of this example. And again, so this is numeric limits. There are many functions that you can call under this namespace. Now, you see, previously I've seen namespace, just std like cout, right? The output stream to console. And here there's actually, you see, you see this numeric limits. Actually, this is a class, or it's a struct, okay? Struct, it's a class-like data type. We're gonna have more to say about structs and classes, but this is just consider this is another type is in the standard library. It's not a fundamental type, but it's a type that's made for checking the numeric limits and a bunch of other properties of numeric types. So you see a little angle bracket here. Now, and for those that you're not familiar, this is the perhaps the first time if you have not used the templates. This is templatized, templated class, essentially, template structure or class. So here we're providing the type to instantiate that template, okay? And so, previously this template is like a blueprint, that's what template means. You know what a template means, right? If you make a PowerPoint, you may use a PowerPoint template. And so once we provide this type, now this becomes a a type that's complete. Template was not complete because it needs to take some parameters, and the parameter needs to be taken for this numeric limits is the type of the the data type you're trying to work with. In this case, we're trying to say here, want to query the minimum value of a short data type, right? This is the fundamental type, which is also a keyword. As you see this color, the blue color here, there's keywords. And so you may query the min value or max value, right? And then there's unsigned int. Okay, we have now explained the word unsigned. Now, unsigned means this integer is always positive. It has no sign, right? It could be 0, could be positive. So that's really what it means. It's non-negative. It's called unsigned, no sign. And so there's unsigned integer here. And then in a minute, I'll show you a full list of the integral data types. So we may also query that, the min and max for that. And then you also query the min and max for long, right? So the long is another integral type, minimum 4 bytes. But again, the actual number of bytes is not guaranteed, and that could change as the computer architecture evolves. And so there's a bunch of other types that we are going to talk about in a bit. Those are the floating point data types. Okay, I just want to point this out here. There's numeric limits. Okay, now back to the slides. So as I said, here is a complete list of integral types in C++ as of now for C+20, basically. So you have on the left, you see there's basically a lot of the sort of equivalent names for the ones that we typically can say that, again, the equivalent type here is more of You may consider it as a sort of a canonical type, but again, it's not necessarily what we usually write though. So anyway, this uh, does not necessarily mean too much here, but the way we write them is again, so preferred typically for those short uh, types that you have essentially you just write short. If you just write short, it's signed. Now you may also have an unsigned short. Now you can just write unsigned short. You probably don't want to add another int in here. Again, just save some typing. And then you have the int, which is signed by default. And then you have the unsigned or unsigned int. Okay, so if you write, these are the unsigned integers. Now you have the long, long integers. Uh, and then long integers obviously is assigned. And then you have unsigned long again, so without the sign bit. So obviously the range of that type, it would be double compared to the signed version, right? And then you have the long long. You have a signed long long, right? Signed long long is signed long long, and then you also have an unsigned long long. Okay. So the long long, you may think, okay, this may be just double the size of long, and not necessarily so. The standard just guarantees that you have a minimum of 8 bytes for long long. Now, as you'll see here in this column, okay, you see this what standard says. The standard says at least 16 bits. And by the way, this here we're talking about in terms of bits. Why? Because a byte, okay, a byte is 8 bits. It's not necessarily always so. Okay, so there are computers out there that 1 byte is not equal to 8 bits. So byte it's a choice in the architecture. Uh, it may not be a bit. So here, anyway, again, the standards want to be unambiguous. So it talks about in terms of bits, then you cannot get wrong. So 16 bits for short, just kind of show you, okay, let's show you this common example for this int. The standard just says for int types, at least you should have 16 bits. Well, it doesn't necessarily tell you how much you could have as a maximum. So this is not, the standard doesn't tell you that. But the standard does tell you, okay, though there's one more thing though. From the top to the bottom, the size of those types are incrementing, okay? So increasing. Basically, the size of integer, whatever you decide in the future, you want to raise them up as your compiler somehow want to do for a particular computer, let's say. Now you have to make sure int is more than a short int, long int is more than int, and long is more, more or equal, okay? So at least that's less than or equal to, okay? In terms of the ranges, okay? So you have the standard specifying the minimum size, but then you also have computers that adopt different data models. Now, these are the names, the short names of the data models, and LP, ILP, IOP. Okay, we're going to explain a bit. LP means long pointer, or 32 bits, and then it also means the integer would be a 16-bit. Okay, so a bit lower, and this is kind of talking about what are the high the data types they have, the sort of the most again, they're talking about a common sizing. So this actually specifies in this type of computer, it has chosen the long to be 32-bit, and the pointer type, and we're going to talk about pointers next week, and that's 32 also. And so in that case, long is 32, and long, again, the standard guarantees at least 64, so that will be 64. And IOP, that's basically int, long, pointer, they're all 32 bits. So that's why you see int is 32, long is 32. Long remains 64, that's the standard guarantee. Then LLP, it means long, pointer are 64 bits. Okay, so long on 64-bit, and then your pointer is also 64-bit. And then in that case, your long is lower. That would be 32. And then you also have the long pointer 64. A long pointer 64 means long is 64, pointer 64, and then your long is still 64. Now, just kind of tell you, okay, what computers actually use those? What about Windows, right? Windows 64-bit Windows right now is actually using a LP64 data model. And then on Mac and Linux and many other systems, actually this is the most common, would be LP64 data model. Okay. Now we have talk about the ranges. Now, for a particular integral type, you have a certain number of bits, right, to represent the data, uh, and of course, that certain number of bits has a limited range. Now, what happens? Let's take could it be is there going to be an issue here, um, in particular to this unsigned int? We'll talk about unsigned int that is a non-negative number, integer number. And that, let's see, this simple example here, like, okay, we have a unsigned integer x initialized to be 20, okay, with a suffix u. Now, if you read the book, for a number, you could have potentially have a prefix, you could potentially have a suffix. Now, this is what's called, when you see just a literal number here, these are called literals. And this literal number, a literal integer here, is a 20 and the suffix u. Now, u denotes unsigned. So we're initializing an unsigned integer variable with a unsigned integer literal. You want to match your data type normally for clarity purposes, or because if you don't, sometimes your compiler may just issue a warning, or certain compilers may just deny, say this could be an error. But again, it may also do a so-called implicit conversion, and sometimes implicit conversion can cause unexpected behavior that you are not aware of, what the compiler actually does it for you. So general word of advice for you when you program, try to make your intention clear. Do not rely on the compiler too much to say, oh, my compiler is going to take care of this. Well, you have to know that different compilers may have different behaviors. If that behavior is not standardized, and then it says, the standard says, well, this is implementation specific, and you just they leave it to the implementation. So then you don't want your program to behave differently when you use a different compiler. So if you can make it clear, make it clear. And then we'll have what they call another integer y. Now, this is a signed integer, means it could be negative or positive, okay? So we initialize that with 30. And then we're gonna basically have an expression here, x minus y. I mean, without even explanation, you already know if you have studied a bit of math, right? So this is intuitive. And x minus y, this is a subtraction. And this subtraction, this between this x and y, is an operator. We'll talk about, previously we'll talk about this less than. That's actually a stream insertion operator. We insert in some pieces of information as an abstraction to a output stream. And now we want to output a value. This value is an expression. This expression is x minus y. And this will be evaluated at runtime. And so how is this going to be evaluated? You have an unsigned integer, 20. You have a signed integer, 30. Now, what compiler will do, though, there are different types, okay? In this case, there are different types, and then what it will do, actually, typically, the compiler will perform an implicit conversion. You know, what convert the operands with less range to the operand to the type of the operand with more range, and the unsigned in has a actually a bigger range in terms of the number uh, in terms of the higher number you can present. And so this is what the compiler will deem in terms of this hierarchy um, of conversion automatically. It will basically say, we'll convert this y to an unsigned integer first, and then do the subtraction. So here's a problem. 20 minus 30 is -10. The result of this expression is also unsigned integer. Remember that conversion it does, or does compiler does implicitly. So that -10 is how is that going to be represented in unsigned integer? Unsigned integer does not represent negative numbers. So that is what the compiler in this case may do is to actually wrap around to give you actually a really large number. That is the equivalent of -10 in 2's complement. And so depends on the size of the, let's say you have 4 bytes of uh, 32, let's say you have 32 bits representing a unsigned integer. And then the -10 would be really just be, in this case, the value that will be the result of it. That would essentially be a 2 to the 32nd, the power of 2 to the power of 32 minus 10. That probably will be the number that actually will be in the result when you print out. In this situation is actually called underflow. Now, because the result -10 is it's below the lower end of the range this data type could represent. And so that basically it's called underflow. It went out of the range on the lower end. So that is a one issue with unsigned integer. And then there could be another issue also. Let's take a look at this one. You have unsigned char. Now remember, char is also integer. The size of unsigned char is typically 1 byte. So with that 8-bit, with that, now we're gonna use by and in the sense of 8 bits when we talk about it. But again, in reality, a byte may not be 8 bits. But then just for our discussion, commonly a byte is 8 bits. So the maximum number could be represented in the unsigned char is we know this from previous table here, right? Well, actually, it's not necessarily here, but again, 256 would be the 256 would be the maximum number that could be represented by one byte, right? So this z plus 5 problem is, if you're actually going to add that up, the actual result would be 258. Now, 258 cannot be represented with that 1 byte, right? It went out of the range on the upper end. It's bigger than the biggest number that can be represented. And what the compiler probably will do is to wrap around, make it a, the wrapping around in the sense that it will, perform a 2's complement operation to determine that value, and the end result would be in this case 258, right? That would be potentially 2 as the outcome. And now your compiler may have different behavior though. That's again, the behavior is undefined sometimes. So don't get into that kind of situation. This is called an overflow, and this is a number that's a little bigger than the largest number representable. This it will basically use a modulo wrapping in this case for the overflow, and modulo 256. So that's again, we say typical, that's how it's done. But again, some of this behavior is not necessarily in the standard, but you're going to see a compiler may do different things. And then we actually talk about type conversion with that example there. There's two types of a type conversion. Um, Implicit, well, we kind of categorize it as implicit or explicit. Implicit means you leave it to the compiler to make the decision for you. Explicit means you tell the compiler what you want. So the explicit type conversion, it's called a static cast. Static cast is actually a keyword. So you can perform explicit type conversion. Now, this static cast, this is a specific type of casting. It's actually a compile time type casting or casting or conversion. Means the same thing, by the way. And then again, we see an angle bracket. So again, that indicates a sort of a template variable situation. And so you remember that numerical limits, it's similar. Okay. Um, this is, you provide the type of the, let's say you're converting from a int to let's say unsigned int, and then your actual variable, you put this or expression, or in this the x minus y, remember, you would put in here, that's the expression. And then you want to convert the result to, let's say, unsigned int, and you will put unsigned int in the angle bracket here. That's the type, the resulting type you want after evaluating that expression. And then let's actually take a look at an example 204. It's more clear usually with the code. Now, this example does sort of a feet, well, actually feet inches conversion. Yards and feet inches. It's converting between those distance units. Okay, so this line, number 6, there's something new here. You see a keyword here, const. You may already know, but again, so const is a keyword, and it means that variable is a constant. So once you initialize this variable with an initial value, this variable can no longer be changed. So it's a constant variable. A typical variable without using const, that means you can keep changing the value of that variable. Once you put a const specifier here, it's part of the your declaration of the variable, then this is a constant, cannot be changed. The compiler will not allow it, essentially will not compile if you try to do it. Okay, so let's say we have a couple of constant, feet per yard, 3, inches per foot, 12. We know 12 inches is a foot, and so on. Then we have a couple of variables. A length is a double. We're going to talk about floating point in a bit. And then here we have unsigned in yards, feet, in inches, right? And let's see, static cast. Is this the example? Yeah, right here. Okay. So first we take from standard input. Now this is the time, okay, we have seen how to output to the console and to get input from your keyboard when you type in some value. Let's say we're getting the value from the user. Now, if you're running, we're talking about this app as a sort of a terminal app, console app. So you can provide the data sort of in the console format. And again, most of the applications you run on your computer on a daily basis, they are GUI type of applications, right? And they interact with a graphical component. And that is a little different, okay? Versus this is taking, again, even for a GUI application, you still also have that the interaction with the application, because remember that main entry function, you can actually pass arguments to it, and typically those apps will do take arguments when it's launched by the operating system. But anyway, so what we're talking type application, that's actually console. We're not talking about GUI type applications here. So we're going to be using this input stream to take a value from your keyboard. You type in, specify the length in yards as a decimal. And so the point I want to make here is I want to just show you the static cast here. The static cast now, this is a double type, which is a floating point type, and we'll talk more about this. And this is a different type. We want to cast that into an integer. It's actually unsigned integer. You know, again, when you do that though, you will lose the fraction of that number. Okay, let's suppose this is what we want. You have to know what you're doing. So this is your explicit instruction to the compiler that this is what you're trying to do. Okay, and in fact, and then you can do the static cast on the expression. This is basically on a single variable, and then you could have the whole expression inside that parentheses as an argument, and then you static cast that result, or converting that result into unsigned int. Okay. And then once you have, again, this whole static cast as a result could be part of a larger expression again. And then we'll actually see a couple of operators here. So we have seen the, well, let me explain a bit more back to this one. And I will have a little more to say about this. So this is called assignment. And we have seen initialization with braces, right, for a variable. And once you have a regular variable, well, we want to do some computation, want to probably change the value at some point. And this is the place where we change the value for yards. So you change the value by assigning a new value. Now, this equal sign could be a little confusing with a mathematical symbol. In mathematics, a equal, they are actually mean equal. Here, equal does not mean equal. It's assigning the value on the right-hand side to the variable on the left-hand side. Excuse me. So that's actually called assignment operator. Okay, it's also a binary operator, means you have two operands, one on the left, one on the right. And you're writing this format. This is called an infix. Infix format means that your operator is in the middle. And there's actually different ways of writing your expression in a different way. And this is a statement, and this is also called an expression in terms of a compiler terminology. It's an expression, and then we'll have seen this is an expression, right? So expression, many things are expressions in terms of compilers. Now, these are the assignments. We're assigning new values to those variables as we make, more calculation along the way in our program. And there's, and then of course, these are kind of a self-explanatory. You have seen, this is a subtraction here between these two numbers. And then you have used the parentheses to organize them. This is more of how you generally understood what looks like in math. And so this is actually a multiplication, obviously. And then there's another thing here, maybe a little strange. That's the percentage sign. And this percentage sign is the symbol that's chosen to represent a modulo operation. And the modulo operation results gives you the modulus of a one number divided by another number, and the remainder of that division is the modulus of that expression. And so this is the what this will give you is that this is called the modulo operation. And so essentially what you see here is, okay, we have the inches per yard times the length, and that is how many inches we have so far. And then you do a modulo operation on how many inches per foot. Okay. Uh, anyway, the end result of that, so you're getting, if you do a division though, you're getting how many feet, right? And the remainder of that, how many feet left over, are the inches that are left over. So essentially, that's what that is. And the book has more concrete examples about modular operation, and go ahead and read those. Okay, so that's what I want to explain about static cast. There are other types of casting, by the way. For example, dynamic cast. Dynamic cast it becomes relevant when we talk about classes and the hierarchy. Okay. And then, of course, you were probably thinking, if you're familiar with the C, what happened to the parentheses with the type inside and in front of the expression, right? This is the old C style casting. And we'll call it C style casting because this is still, again, this is the way to cast in C, but this is not the way to go in C++. And because this could be dangerous, and it means trying different casting mechanisms in a particular order, and then just to see which one succeeds. And it will give you some result, but sometimes it may not be the one you want. So you want, as I said, you want to make your intention clear. In C++, this operation, this casting, the C-style casting has been differentiated into a few different ways of casting. As an example, we have a static cast, we have dynamic cast. There's actually even more. And this is not very safe and not recommended at all in C++ programming. So as I always actually tend to say, if you're writing C++ programs, don't try to use all these a lot of old C styles features. A majority of them, if not all, have been replaced with better facilities in C++, and try to learn to use them instead of going back to C. Even though it's largely compatible with the C++, not with the C, not 100%, but by a huge portion of C is compatible in C++, but doesn't mean you should use them. Okay. Floating points. So the floating point is essentially, okay, we have seen numbers, you have integers, and what happens to those fractions, right? The, pi, 3.14, how you represent that, that's called a floating point, where you actually have a decimal point in your number. So the floating point, now, why is this something tricky? In computer, as we know, it just comes down to zeros and ones for every bit, right? Then you group multiple bits together to make something out of it. Essentially, the computer doesn't really know what is a floating point. It doesn't. That's not what the computer deals with. The computer just deals with the zeros and ones in those bits and the bytes. So the way we do this, of course, we assign meaning to the data that's in those bits and the bytes, and so we can actually say the way you arrange the data in this particular couple of bytes will mean something we call floating point. We want that to represent a fraction, for example, and so then you have to kind of be very specific. How do you interpret that, right? Which bits are for, uh, let's say you have a scientific notation of uh, a a large number that, and then you have sort of the mantissa part of it, or it's called a significand, and you have the exponent of that scientific notation. And here's an example of scientific notation, by the way. So 1.18 times 10 to the power of negative 38. This is a scientific notation of a large um, decimal number, right? And we how do you represent this in zeros and ones? So what we do is we use some bits to store the significant, and then we use some other bits to store the exponent. And that's really what the idea behind. And then the how many bits exactly, how they are arranged, and where's the sign bit, for example, right? And this is all laid out in that standard. I believe it's IEEE standard, 754 or something. So that is standardized how to represent floating point types in the computer. So that's basically what all the major compilers are using. And there are three types. The last one is less common. You've seen the float and double. So again, the precision, we're talking about how many decimal points could be represented by this type. So double is almost double precision. That's kind of what the name comes from. And so you have float, and you have double, and the float, I believe today typically is a 4 bytes, and then double is typically 8 bytes. And then you have long double, which also is typically 8 bytes today. It could be longer, but again, so you have in some compilers they're actually the same. But so again, see these names are more of sometimes compiler specific. But again, there's a minimum imposed by the standard, just like the integral types. And then we'll see the range of those numbers can be represented in those types are those pretty large. There is a trade-off between the range, how big the the range is in terms of the largest number or smallest number you can represent in the universe versus the precision you can provide, right? So when you represent a large number and small number, there can be gaps. Now, just remember all the zeros and ones in those bits. We cannot represent every possible number. And again, the real number is infinite. So there are actually gaps in between two numbers that can be represented in those data types. It's not contiguous. So, but most of the time it'll be okay with a little loss of precision, for the purpose of. Now we have to be very careful in computation, by the way, when you do arithmetic on floating point. If you're not careful, you could get something wrong or unexpected result. So if you're doing something that's a well-known operation, try to use the libraries out there instead of doing this on your own. You can easily make mistakes there. So now with the floating point, there's one particular thing that comes out. We know, okay, what happens when you divide a number by zero? If you divide a number by zero, you get an infinity result. The infinity result, okay, again, that number needs to be represented in memory. For example, the way it's represented, a common mechanism would be like, say, a significant is all zeros, right? The bits representing the significant is all zeros, and the bits representing the exponent are all ones. Right? That's an example. So those are part of the standard for floating point representation. The IEEE standard will have those things, and that's why we need a standard. So certain numbers are reserved for representing infinity. And you could have potentially positive infinity or negative infinity. This is the things. Again, they have to be represented differently in the actual number that is reserved for representing infinity according to that standard. And so when when you're doing computation with the floating point numbers, you may encounter, if you have an error, by the way, that usually means erroneous situation when you get infinity. If it doesn't, of course, it's meaningless, right? So you could also get another type of result. It's called not a number. Not a number. This for example, 0 divided by 0, or you have infinity divided by infinity. You get not a number as a response. Okay. So let's sum up of some of the basic operators we have seen so far. We have addition, right? 1 plus 1 equal to 2. Yeah, this is a very the arithmetic couple of things, right? You have subtraction, you have multiplication, you have division. Now this subtraction, I've also mentioned here, this negative symbol, this negative sign symbol, it can be used for a subtraction. It depends on the context. If you have an integer or floating point, a minus b, and that's a subtraction. But then if it's used in a context that shows it's a unary minus situation, right? For example, you have a number a equal to 1, and then you write an expression negative a, and that negative a, the negatives right there is a unary minus operation. Okay, unary minus operator also, because in this case, unary means you have a single operand instead of a binary that you see with a subtraction. Okay, and then we have seen modulo, the remainder of a division, and we have assignment, right? Remember, this equal does not mean equal in mathematics, and the actual equal in mathematics would be actually double equal. We're gonna see some of those. It's called the relational operators. Um, and then there's another type that is sort of a shorthand of two operations together. Let's say you have a plus b, and then you're gonna assign that result back to a, right? And this is what this is for. And then you would just write down, say, plus equal, a plus equal b. That actually means a plus b, assign it back to a, okay? A is on the left-hand side. So this is what it really means. This is called a compound assignment. This operator with a assignment equal assignment after that is a compound assignment. So essentially, when you write left-hand side, operator equal, like for example, plus equal, right-hand side. And what that really means is left-hand side, we assign the, okay, just in terms of when I read it as equal, it does not really mean mathematical equal. So what you do is you have left-hand side perform the operation with the right-hand side in parentheses. Then you assign the result back to the left-hand side. This is really what this compound assignment will actually do, okay? The difference between division and the modulus, in fact, this is what the book calls modulus operator. To be more precise, it should be called a modulo operator. In terms of the operator, it's called a modulo operator, but the actual result is the modulus. Okay, that's a little bit difference there. So the divide operator, that is, here's an example: 11 divided by 4. Now, keep in mind though, these are the integer division. It may not be what you expect in mathematics. In mathematics, you get a fraction, right? But there are integer types. You don't get fraction here in computer, in C++, the way it's defined. So what you do is instead you get a 2. Okay, 11 divided by 4 as an integers, you get 2. Why? Because you divide this in 2 times, times 4 is 8. You have a remainder of a 3, right? So 3 is the remainder of that division. And this is discarded when you do the division integer on integer. Now, the modulus is doing the other part. Instead of discarding the remainder, it takes the remainder by discarding the quotient, okay? And so that is, as you see, these two operations complement each other depending on what you need. This is a very useful operation, by the way, in implementing certain algorithms. And a couple more basic operators that we did not have an example to show for, and so the book did mention those. So this plus plus this plus plus is a increment operator. This essentially increments the value by one. Now, you could use this on integers or floating point. Essentially, just increment this by the value of the variable by one. Use this together with a single variable, not with an expression. It has to be on a variable. And then, okay, you see this is a unary operator, right? It was a single operator. This could be put before the, in terms of when you specify it, it could be before the variable or after the variable. So this is actually two forms. This is called a prefix form or postfix form. In the prefix form, if this plus plus variable a is part of a larger expression, and this means if it's a prefix form, the value of a will be incremented first, and that new value of a will be used to evaluate the rest. Okay, if it's a postfix form, say a plus plus, and then in that case, the value of a unchanged will be used to evaluate the rest of the expression. And after that is evaluated, done, the statement is done, and there's an additional operation to uh, basically then increment the value of a by one. That's the postfix form. And then the decrement operator, again, is just decreased by one. It's analogous to plus plus. And then we also have the size of operator. Now, size of operator is an operator too, even though it's written in words. It's also a keyword, and this size of can be used to determine the size of objects or types. Let's say you want to know the size of an int. We'll talk about typical is 4 byte. Then you can find that out from a compiler by just print this out, see what this gives you. So the size of can give you the size of object or type in bytes. Okay, and so here we're going to be using sort of again, this is going to say, well, the normally use the meaning of a byte in equals to 8 bits. That's what this will give you. Now, we also have seen the stream insertion and stream extraction. Okay. However, the same symbols also can be used to mean other things, and it's contextual. This could mean left shift, and then the double greater than sign can mean the right shift. So this will be explained in the next chapter, actually. And so they are the bitwise operations that you operate in sort of in a bitwise fashion. And so for now, just know that these symbols could be used to do the stream insertion or the stream operations, or could it be a bitwise operations? Okay, so that's what I have to say about the um, integers as a on the floating points. These are numbers that in the as a fundamental data types of C++. Thank you.